Thank you for joining the Once Changing the World, which is India's first future tech meets sustainability podcast. And today I'm delighted and honored to have with me Mr. Srinivasa Chakravarthy, who's the professor in the Department of Biotechnology at the IIT Madras. And his lab, the Computational Neuroscience Lab, is working on modeling the human brain. He has authored two books, Demystifying the Brain, a Computational Approach, and Computational Neuroscience Models of the Basal Ganglia. He is also the inventor of a novel script called Bharati, a unified script for Indian languages. So, sir, really appreciate you taking time and being part of a humble podcast. Why don't we start with a brief introduction, your background, and why computational neuroscience? What is the subject? Maybe you could possibly share light on computational neuroscience also.
Okay, great. Thank you very much. And first of all, really, I want to thank you for this invitation and for this forum where one can express one's ideas and opinions. So, my background briefly, I have a BTech in electrical engineering from IIT Madras. Then I did masters in biomedical engineering and PhD in computer engineering from UT Austin, University of Texas at Austin. At that time, it was in the 90s, and neural networks were just becoming popular. So I done my PhD on that topic. But at the end of PhD, I felt that this is not how brain works. I mean, neural networks are apparently inspired by the brain, but that's not how probably brain works. So I said I need to learn more about brain proper. So that's why I went for a postdoc in neuroscience in Baylor College of Medicine. I worked with this wonderful teacher called Reed Montague. He was a very inspiring young researcher at that time. And he really kind of set my feet on the course of computational neuroscience. I said, this is what I'll be doing all my life. So after coming back to India in 2000, I started my own activity. That's how things happened. So talking about computational neuroscience, brain is a physical, organ, like it's a piece of physical matter. So you can apply laws of physics and chemistry and describe its activities. And it's a network of these cells called neurons. And neurons are basically electrochemical entities. So you can apply, the physics of electricity or chemistry, equations of chemistry to describe its function. So, for example, neurons exchange signals through electrical voltage pulses. So these pulses travel along the fibers of neuron. The neuron is basically a cell body and a bunch of wires sticking out. So you can use something called the cable equation to describe how the signals propagate. Or in terms of chemistry, if you want to study the activity of a molecule like an ion channel, you can apply laws of chemistry and write down equations and describe them. So you can model brain at multiple levels, right from single molecules or single channels and so on. You can model chemical pathways in a cell, or you can model whole cell. Because single cell itself can be very complicated in the brain, right? Well, for a single cell, you have something called compartment models, where you can divide cell into many parts and so on. And then you have systems where you can study the whole visual system or the whole motor system and things like that. Then you go to whole brain is difficult, but that's a big challenge now. And ultimately, to explain behavior, right? Why does a person behave the way he or she behaves? So this is the kind of a big spectrum of computational neuroscience.
Human brain, I think it's one of the most fantastic organ, and the things that it does is how it does is still a mystery, because some of the top researchers, neuroscientists around the world are kind of trying to figure out the language of the brain, how it gives rise to the five senses, the perception, sight, sound, touch, smell and taste, how the firings of the neurons, firing and wirings leads to all of five senses. I mean, we're getting closer, but we still quite far away, like you mentioned, of understanding the human brain, but there are there are various researchers, labs, academia trying to understand the human brain and possibly decode a language of the firings of neurons. And once we do that, I think we will be able to possibly map it onto the computer, and maybe that would be because there are a lot of these companies like Kernel and Neuralink who are trying to take that approach. Now, I mean, for the listeners who really do not know what is the frontier or the cutting edge of understanding the language of the brain, could you kind of break down on how do we do that? What's the current technology stack to understanding how our brain functions, fires and wires?
That's a very great question, a question very close to my heart. Let me talk about from my perspective. Right. First of all, we need to distinguish between data and understanding. The understanding comes from the understanding of fundamental principles. Right. Data comes if you have sophisticated technology, you can generate data. So what is happening in neuroscience and probably in biology in general these days is, in fact, even other branches of science, the trend is to generate a lot of data and constantly develop more and more sophisticated technology to generate data. Because we're living in a big data era, right? That's what everybody's talking about, data. But what happens when you have just a lot of data and not enough insights into the data, or what one could call deep theories, which can link a lot of data into a very neat outline, right? You'll just end up with data without understanding what the data is saying. So that is what is lacking. You have lots of data, but deep theories are somewhat scarce or somewhat weak. I mean, I'm not saying this. Top people like, for example, V.S. Ramachandran talks about this problem. He says we are in the Faraday's age, right, of neuroscience. In the sense, we haven't yet reached the Maxwell's, James Clerk Maxwell's age, where we had the Maxwell equations, which will unify electromagnetism and all. So we are still very empirical. I mean, unless we make that progress, behind all this glitz of modern neuroscience, I think there's something hollow. We need to fix that by developing the right kind of theory. And then this field will just take off like anything. To give an example, to give a perspective on that. Then there's so much is being talked about neuroscience and so much money is being pumped in neuroscience. Tell me one neurological disorder, big one, that we can say we can cure. Right? Not massage it, not manage it, but I can cure it. The way you can fix a fever, right? Or a malaria, something like that. There's a fundamental problem because the traditional approach to disease is a germ theory. You have a germ behind the disease, you kill the germ, disease is gone. But brain disorders are not like that. They're very deep dysfunction of the network. So you need a different kind of approach. So I mean, that's what I'm saying. That is the target. Then we have to change the orientation quite radically.
We sitting in 2022, the research field of neuroscience, we've been, there are so many people who are like working on it, academia, entrepreneurs, scientists, researchers, but you said, sadly we do not have one single cure. What are your insights? I mean, what are your insights? How do we get to that understanding part? How do we get that? Do you have an insight or maybe like a rough roadmap on getting to that point where we kind of not just look at the data, but pass the data and make it into intelligent insights that works into finding something which is relevant?
Yeah. So it is a very difficult question because obviously there are really brightest minds are at work in this, and I don't want to say something pompous and I'll give you an example again from history of science, physics, astronomy. So when Kepler was analyzing planetary data, he had this preconceived notion that somehow they would fit into this what is called platonic solids, the size of platonic solids where each can be embedded into the next one and so on. So he tried with that, and for a long time that didn't work out. Then he assumed that the orbits are circles. It didn't work out. Then just by fluke, he said, okay, probably they're ellipses. Right, and that completely changed because paradigm has shifted, right? And then sun is a focus, no more, because the Greek idea of perfect forms and godlike perfect forms, all those nonsense, had suddenly was dispelled completely. So moment he made that shift, things just fell into place, and all the planetary data could fall into three patterns, three Kepler's laws. When Newton saw that, he could see even deeper law in that. There's a centralized force field called gravitation. It follows inverse square law, and so on. So what I'm saying is, how did that happen? How much funding went into it? Kepler was literally a beggar all his life. I mean, he was living hand to mouth, very poor guy. But how much funding did he have? How much funding did Newton have? 1 year he was sitting in Woolsthorpe, because there was plague in the country, and the students were kicked out of Cambridge. He went home, sitting at home, and just worked out how much funding did he have. Right, without that progress, with the traditional astronomy of Tycho Brahe and all these guys, how far would we have gone? Tycho Brahe had a lot of funding, and he had huge observatory. He didn't want to share his data with Kepler. There's a lot of politics between them. Because Kepler is a small fry. Tycho Brahe is a big guy, funded by the by the king and all that. Right? Who finally brought real progress? Tycho Brahe or Kepler? Who with no funding, a very really poor guy. So what I'm saying is, I don't know what it takes, but that's what it takes. You see, how did the Kepler and Newton manage it? That's what it takes even now. It's no different. Right? It's not a question of how many billions you're pouring into it. How do you bring in that kind of a? I don't know what it takes. That's what it takes.
I think even today's world, somehow the best innovations are happening in small teams rather than those big insights, the big companies, because these big companies, when even the way you work over there, everything is hierarchical. You create something, there's so much politics over there, and the patenting process, and yeah. So since you mentioned about the politics of the industry and the funding, would you like to shine light on that? How is India placed? What's the ecosystem support? What's the ecosystem support that you getting? Are you happy, not happy with the play? Would you expect something more?
Yeah, this is also a big question, but I'll make one observation which I've been seeing over the last 20 years. See, because I come from IIT Madras and I studied in IIT Madras, and in all IITs, we didn't have a strong research culture until about 10, 15 years ago. And people were doing research, we were producing PhDs, but it's not like a huge thing. So something that you do like as an aside, right? You mainly teach courses, but once in a while you do something. So that was the thing. But in the middle of last decade, or 2005, 2007, suddenly a lot of new faculty have joined. These guys were all trained abroad, and they were trained to do research on a day-to-day basis. It's not an optional thing for them. So the culture suddenly changed. Like, research is normal. That's what you do all day long, in addition to teaching. So that is a good thing. But what happened very quickly is West has gone through a whole trajectory of research over 400 years. For us, it's like they really pushed into it, thrust into it. Like just a couple of decades ago. I mean, before that, the stalwarts used to do it, but otherwise, it's not a novel systemic thing. Therefore, in the West, what happened? We suddenly got the era of quantification, research quantification, number of papers and H index and all this stuff. So we also quickly adopted all those methods. Thing is, when you have a living fundamental research culture, and which is growing and very vibrant, and at some point you want to measure it, that makes sense. But we are just starting, right? There is no real deep, prevalent research culture, right, of thinking and debating and all that stuff. And just you want to put this quantification, that immediately puts you in a very rigid framework, and you do anything outside the framework, you're screwed. So, but world over, this is our situation. This is a fact of the academics in the world. So only thing is, then the only way you break this or beat this system is you do it on your own, risking your career and said, no, I don't like this system. I don't care what will happen to my career and my ladder climbing. Well, I think it's stupid, and I'll do my own thing. Whatever happens, happens. Right? This is how one can try to do something really nice in this framework. But otherwise, framework is too restrictive. And we are shooting ourselves in the foot by sticking with it very rigidly. And there has to be some flexibility. We need to go deeper into it, look at the spirit of science, and then see what kind of flexibility we need to offer so that you can come up with real innovative, creative stuff.
Right. I think the structured functioning needs to break out because I guess there we kind of cage or great minds into these boxes, and we set boundaries on how it's supposed to do. But like you said, somehow the most awesome innovations happens when it's unstructured and it's free, where it's debate. When you debate things, and the debating environment is open rather than saying, oh no, I'm right and everybody else is wrong. I guess the learning open science culture is something which needs to be breeded for us to create India which is with great innovations coming out from here. Now
Actually,
sorry,
I want to add one more point about this India and science, because Indian culture and traditional culture and debating, right, which is necessary for science, they don't match well. Like you said, in India we have a very hierarchical culture, right, and we have this buzurgo and who are seniors and you're not supposed to speak in front of them. Right? So with that kind of a culture, you cannot openly, oppose. If the senior guy is saying something that you feel is wrong, and then you counter that, you'll be in trouble. All right. So there's a social yardstick and the scientific yardsticks are totally different. Even with my students, I give them so much freedom. I say something, what do you think? You think is stupid? They're all silent because they don't want to say something against the teacher. It's considered disrespectful, which is rubbish, of course. In science, it doesn't work that way. So it's a very deep set problem, and it is going away slowly, but youngsters are very different. The millennials are thankfully made of very different substance, but it is taking time because there is a conflict.
So you are the senior professor. You are the founder of the Computational Neuroscience Lab, and you're working on the MESOBRAIN project, which you're working on modeling the human brain. Could you talk about how do you go about doing that, modeling the human brain? What's the tech stack required or learnings required to model the human brain?
So in the beginning, we didn't start out with this idea of modeling the whole brain, the mesobrain or anything like that. So we just accidentally started working on basal ganglia. Because a former student of mine called Sridhar Devarajan, who is now a professor in IISc neuroscience, he was a student in aeronautics department here. He said, I want to work on this problem called abulia. It's a disease, it's a will disorder, related to basal ganglia. I said, I've never heard of this, but sounds interesting. Let us work on it. So we started reading together. I mean, I had no idea what it is, and he also didn't have any idea. He just heard about it from somebody else. That's how the journey began. And one thing led to another. And since I was not part of any of the standard camps working on basal ganglia international, we were doing something very stupid, very naive, and on our own. So we took off in a different direction. And we didn't know what we were doing until about 2010. This began around 2002, 2003, maybe. Until about 2010, we didn't know what we were doing. We were doing something, but we could see a pattern coming, right? And then we see it's a slightly different theory of basal ganglia. And then we started getting more confidence. We kept developing it. Things started falling in place, and more consolidation happened. Then we said, look, if this is how simple basal ganglia is, right? Why not take similar approach to other systems like hippocampus? And we began work on hippocampus around 2015. And there also we were able to develop this kind of a unified model, which can explain many aspects of hippocampal spatial functions of hippocampus. So with that, we started getting confidence that, look, at this rate, we can develop a simplified model of the whole brain. I'm not talking about a super detailed model, which is very hard and so on, but a simplified model, like a cartoon model of the whole brain, that can be done in a fairly, maybe 10 years. 5-6 groups can come together and kind of they accept this approach. It can be done very quickly. So, and I am a big fan of the work of Walter Freeman at UC Berkeley. Right, he talks about his mesoscopic level and all that. I met him several times. I really admire that. He passed away recently. So I said, okay, let us call this a MESOBRAIN. That's how it happened.
Since you mentioned about abulia, now while building this, modeling the human brain, how is interrelated? How is it creating an application over there and so creating a cure for abulia, or maybe talk a little bit more about that. Share light on
Okay.
what could be the healthcare approaches once you are able to model it in a way where it creates solutions.
So, for example, abulia is related to basal ganglia, right? So we began modeling basal ganglia, and particularly with the interest of understanding Parkinson's, because that's another major disorder related to basal ganglia. So after this, about 10 to 12 years of effort, we had this kind of a unified model of basal ganglia. Now, basal ganglia is a subcortical circuit which is involved in lots of brain functions. And so if you can group all brain functions into 4 major domains. So sensory motor function, cognitive function, affective function, or emotional activity. 4th is autonomic function. How do you control the internal organs? So damage to basal ganglia can give rise to impairments in all these 4 major domains. So it's a very high level in hierarchy. This is the circuit. So we were able to develop a model which can explain a lot of its motor functions, right? And some cognitive functions like decision making, working memory, things like that. And it's still going on. We're still developing the model for that. Now, after doing a lot of this fundamental modeling effort, I said, we need to focus more on application, especially modeling, because we have done a lot of disease modeling. So then I started thinking about what kind of applications are relevant for Parkinson's. So if you look at PD or Parkinson's, there are 2 major classes of applications. One is medication, right? The other one is deep brain stimulation by surgery. which is a very invasive procedure. And so we developed a model of deep brain stimulation. So that is, thing is when you put electrodes in a part of the basal ganglia called subthalamic nucleus, right? What currents do you apply and what current amplitudes and what pulse width and all that is empirically decided. There is no computational logic to it. So people are developing models. So we developed a model too, and to explain several functions, several effects, that observed effects of deep brain stimulation. Then another major class of applications is medication. So a normal medication is L-DOPA for Parkinson's. So we developed a grand model. This is called this is a multi-scale model, which the model is designed at multiple levels, at molecular, chemical level, then cell level, circuit level, behavior. So this model will explain what will happen when you take a bit of L-DOPA, right, and how will it affect your behavior. So apparently the many pharma companies are trying to build such models, because what happens is when you give a medication, you're trying to understand what's the effect of the medication on the symptom, right? So if you can model that whole thing, all the intervening levels using a mathematical model, and that will make your life easy. You can save on the number of clinical trials you will have to do, right? You can save a lot of money by doing. So there's a big push to develop these kinds of models. So and the second thing is, even when it comes to actually diagnostics, I feel there's a reform that has to be, that has to happen, in the sense, if you look at Parkinson's, right, PD, the way you rate the PD severity is something called UPDRS score. So Unified Parkinson's Disease Rating, etc. So that is very observational, subjective. The doctor looks at the patient and says, okay, for motor function, I'll give a rating of 3 on 5 or something like that. But whereas, imagine what will happen if you took quantitative data from the patient. The patient comes to the clinic, right? You ask the patient to write something, because PD patients have what's called micrographia, they write small letters. So you can take a recording of that on a smartphone and then measure the size. Or you can let them speak, record their speech samples, let them walk, right? Let them play a decision-making game, and so on. So you can take all this data on a simple smartphone. It doesn't need costly equipment. And you analyze this data, then there itself you can do a lot of data analytics, and when you can even start startups just based on this bag of tools. But I want to go even one step further. Use all this data and plug it into a computational model, like the kind that we have developed. Then the data will translate into certain meta parameters, right? Very high level parameters. These parameters will define the condition of the patient. They'll let you locate the patient in the space of the disease, right? And of the disease parameters. Then you have a patient-specific model. So then whatever treatment you want to give, how much L-DOPA and with what frequency and all that, you try it out on the model first, right? And if the model approves it, you give it to the patient. What combination of drugs, right? So this is kind of putting the whole therapeutics on a computational platform. This is the whole idea, but it's a very hard problem. We need a lot of help from clinical people, and it's a long haul. But we are doing something similar for stroke right now. We have a multi-institutional project funded by TCS, partly by government, and with Sri Chitra and NIMHANS and IIT Hyderabad. It's a big project that we are doing. Once we do it for one or two diseases, it becomes a kind of a streamlined process. We can do it more often.
It's a long shot, but eventually when we are able to keep on modeling small the parts of the human brain onto the computer and creating the simulation, trying to understand what's the pros and cons. You mentioned it works in treatment, diagnosis, and so on and so forth, and so it's an exciting space. How computationally intensive it is to build these models, and like you mentioned, you partnering the government, things like that. What are the collaborations at this point in time? Are there something that you're working on which you can talk about? Because these are now at a very nascent stage, but I think when you collaborate with the industry, the stakeholders, you will be possibly be able to create lot of healthcare applications and solutions in the near future.
So this particular project I was talking about on stroke and rehabilitation, this is funded by TCS and partly by government. And so this project combines 3 technologies. One is computational modeling, then neuroimaging, then clinical work. So the idea here is people have been trying to see if gaming can improve stroke rehabilitation. So when person has a motor stroke, right, they're given some repetitive exercise, which can be quite boring. They may not comply with the exercise regime. But if it's like a game, if it is gamified, then they would love to play the games and they'll get better as a play. Thing is, the evidence on this is somewhat kind of sketchy, and there's some studies say it might matter, some studies it doesn't matter, just like as good as the traditional therapeutics and all that. So we have developed a game. Initially, we wanted to develop a virtual reality-based game. Then we felt it's too cumbersome because the guy has to wear the headgear and all. We developed a simple game which you can, and it will run on a laptop. We don't need any fancy equipment. Then we also developed a model, a computational model of stroke, right, where we took a very simple, what is called a convolutional neural network, and divided into two halves for left brain, right brain. And then we asked a lot of fundamental questions about stroke. I mean, the thing is, in neuroscience and even in clinical neuroscience, there are these kind of orthodoxies, right, where we say, oh, this is how we should do it, this is the best way, but how do you know, right? Okay, because the 10 case I've seen this method work best. So can we put these ideologies to test in a computational model and come up with a synthesis where we can say that under these conditions, this approach is best, and under these other conditions, we want to synthesize all these different schools of thought into a grand framework, right? So we have done that. We have published 2 papers, one in scientific reports. The second one is still under review in Journal of Neural Engineering. So that is a computational thrust. The third thing is neuroimaging. So the thing is, you need to know if the brain is recovering, stroke brain is recovering, then you can see it in the activation patterns. So my colleague, Dr. Bapiraju in IIT Hyderabad, he is an expert in neuroimaging. So he's helping us with that. And then we have colleagues in Srichitra, Dr. Sailaja, Dr. Keshav Das, right, and Nimhans, Dr. Sijitesh. They're all helping us, right, in doing the clinical work, and their expertise in stroke is really tremendous. We're putting all this together, and hopefully, if we succeed in creating a very nice pipeline, a gaming system with all the data processing and so on, we want we want to start a startup with help from TCS. And where then the startup will work with clinicians and put the patients on this gaming system, and model will tell you what is the how to tweak the parameters of the gaming or customize the gaming to the needs of that particular patient. So we want to perfect this pipeline so that it's a different kind of a rehabilitation.
Lovely. I hope that more of these, you researchers, academicians, tie up with the industry stakeholders and build these products and solutions and take it to the market. Because what happens that I think I always see this, that these entrepreneurs are CEO of the companies who take these ideas, and the ones who are actually behind the backbone of the ideas are always lost into the ecosystem. So I hope that there's more researchers out, such as yourself, who are supported by the government and the ecosystem to take this product to the market, so it's more honest rather than blurring with the economical benefits. Because I think what's happening so far has been the entrepreneurs always try to create businesses which is profit at any cost, and they don't look at the solution holistically, whereas somebody who's been at the core of building and developing the product will always look at the product in a holistic way, not just with the linking it to the market. What's the cutting edge of innovation in the space of human brain modeling? Mr. Makram from EPFL, the Blue Brain project, is building something like that in similar lines. Are there anyone else that you would like to shine light upon? Are there people that you look up to in the space who are doing some cutting edge things?
So yeah, Professor Markham, I've met him once when I visited the Blue Brain project in Geneva, and it's a fantastic project, very ambitious. So Professor Markham says we don't model the brain, we reconstruct the brain. It is very ambitious, very hard, but they have the resources to do that kind of thing. In fact, my former student, Dr. Vignan, has joined that center as a postdoc and doing some work. Now, the another group headed by Chris Elias-Smith in University of Waterloo, they have developed a framework, for developing large-scale models of the brain. And I like their approach, and it's very interesting. And and more recently, I was just looking on LinkedIn. Uh, Jan LeCun, who did the very first model of convolutional neural network, he's proposing a certain approach to brain modeling, and he wants to work on that over the next 10 years or so. It's more like a futuristic thing. So now one big game now is to model the whole brain. I mean, there's at various levels with various approaches and so on. So large scale models are the in thing now. In India, there are a lot of colleagues who are doing very interesting work. For example, Upinder Balla in NCBS, or Rishikesh Narayanan in IISc, SP Arun, then Baipi Raju, IIIT, Rohit Manchanda, Shyam Divakar. These are all my friends, right? Suvita Nathkarni and Collins and so on. A lot of interesting work is going on. But again, what I say is, I'll repeat, I think the real progress, and which I don't know how it will happen, is if we can make progress in that at deep theory level, because the framework that we have now, so there are some ideas which are very deep principles, like the idea of Hebbian learning. You see it happening in the brain in many forms and many species and so on. It's an example of a deep theory, a deep principle. But I don't know, at the end of my career, if I can see something like the 10 laws of the brain, right, and each mathematically definable, I think I'll be very happy. I'll retire as a very happy person. So I think that's what has to happen. Otherwise, we'll just keep plodding around and then keep trying to go.
Neuroscience, AI is very, very linked. There's a lot of people. There's one approach, like you said in the beginning of the conversation. There's a lot of these large neural networks, language models. It's a very data heavy. And they're doing some great things. We have GPT-3, Gato, OPT 175B, and there's really cool. These large neural network language models, but they depend a lot on data. The other side is the approach to artificial intelligence, the cognitive approach where they're trying to model the human brain itself. How would your research apply in possibly accelerating artificial intelligence? And do you think that we could be someday creating machines which would have human level intelligence?
Yeah, very deep and extensive, large question. Okay, let me try to answer that best way I can. So if you look at AI and computational neuroscience, right, you can think of them as two extremes on an axis. So take your deep learning approach, right, with reinforcement learning or supervised learning, all that stuff. The other extreme, you have something like very detailed neuron models, where you model single fibers and the cell body and ion channels, that kind of thing. What are called biophysical models. Now, there are lots of shades of modeling in between the two. So thing is, although the deep learning networks were originally inspired by the brain, after some point they said we know everything and we don't need to look at brain any further, because we're getting after the 2005 deep learning paper by Hinton et al. It is kicked off a revolution, right? So in fact, recently somebody shared an article saying that AI is done. We are done. All that we have to do is just train networks on more bigger and bigger data sets, and we have achieved whatever is there to achieve. There's nothing more to learn from brain. But the same networks will make very silly mistakes. In fact, one of the authors says, if my child makes this kind of a mistake in recognizing a yellow light as a green light, I'll take the child to the doctor immediately, to a neurologist. So we are not done yet. In AI, we are not done. We have a long way to go. So then you have to look at inspiration look to the brain for inspiration. But what will you gain from brain? I think two things. First of all, the architecture. So the deep network architecture, the architecture is nothing like the brain. Just input to output, a long pipeline or multiple inputs and so on. Brain, mammalian brain, especially if you take, there's a very typical architecture. There are sensory streams going in, there are motor streams going out. There's a huge decision-making area, and there's a big sensory motor hub through which lots of connections go in and out the thalamus. There are all these major loops, cerebellum, basal ganglia, hippocampus. The huge memory system. We don't know how it works fully, right? And so we need to understand at least the essence of this architecture. We don't have to copy it, neuron by neuron. But what is the essence of the architecture? We need to understand. Why is Nature has taken billions of years to work this out. You can't just ignore that, right? You need to understand. The second thing is about the dynamical elements. The elements, the fundamental units of brain as opposed to fundamental units of the deep networks. Deep networks are basically, you can say, two kinds of neurons, right? One is simple sigmoidal or static neuron, input-output which are input-output function. The other kind of a neuron, if you want to produce dynamics and have memory, is the LST. This is a workhorse for all recurrent neural networks for sequence processing. But whereas if you look at brain is full of oscillations. It's an oscillation engine. Such rich tapestry of oscillations you see in the brain. In fact, we began collaborating with Dr. Georgi Buzaki. He's a very big name in neural oscillation. He's at NYU, New York University. So I feel even in computational neuroscience, forget about AI, we don't have a grand theory of oscillations. We have only, again, a patchwork of models, right? So thing is, if you can see oscillations in deep networks, that day I will say that deep networks have taken a major step forward. Okay, I think for that you need a very different approach. You need to borrow ideas from communication theory, ideas of modulation, multiplexing, frequency multiplexing, and coding, and then ideas from signal processing, filters, and all that. So if that is not, that's what actually we are working on right now. That's why I'm talking about this like that. I'm talking to people in electrical engineering department here. Look, can you guys help us with some of these problems? I have only a vague idea, but how do you make it concrete and write down equations and all? If you can do so, if you can put oscillations in deep networks, I think that would be a major step forward. The second thing is, if you can at least create a rough architecture of the mammalian brain and design agent models, right, based on that, that will be something. And that's not very difficult to do. Maybe 10 years we can do.
Right. Yeah, exciting space. I hope that the research space throws away its siloed approach, and even the entrepreneurial industry, and collaborate and work together, because there's, like you said, the only way to accelerate this is join hands and take an interdisciplinary approach to creating a solution. So I hope that we in India and in some you guys, the team, the Computational Neuroscience Lab, is responsible for possibly modeling the human brain. Now, where does one start? Supposing if there's a student, somebody who's interested in computational neuroscience or understanding how do you model the human brain, where does one start?
I think the best way is, especially if somebody is coming from engineering, that's easier. As an engineer, it's easier to understand brain than I think you're coming from classical biology. You just pick up some ML and neural networks and artificial neural networks, because that's how I began my journey and made a side door entry. So once you know that, once you understand how a network works, so what is a hierarchy and multi-layer network, how it works and all that, you can easily put some biological kind of a interpretation of that and slowly get into neuroscience. In fact, I have a course based on that called Demystifying the Brain. It's a short 10-hour course in NPTEL. So people can take that. And I also have this book, the course is based on the book Demystifying the Brain. The other books, like, my favorite is a book called The Computational Brain, which came, I think, in the 90s, late 90s sometime, by Sejnowski and Churchland. Beautiful book. It's actually inspiration for my book. I really love that book. With that kind of entry, then slowly the student can get into a research topic and then get deeper into it. But it's, right, I think it's pretty straightforward to get into neuroscience.
What's the roadmap for you, your lab? What comes next?
So I'll talk about more general roadmap, because always I think vision goes far beyond your personal capacity. Right now, as a person in charge of a lab, and my own network is still, is quite small. But I'll talk about what can happen in neuroscience in general, in computer neuroscience in general. So first of all, like I said, this marriage of deep learning and oscillator theory and communication theory, signal processing, this can happen. That'll give rise to a hybrid kind of models, which can be very powerful both in AI and in modeling brain. So that is a purely computational exercise, a theoretical exercise. So I think that will lead to some kind of an oscillator theory of the brain. That, like, it's like a mirror with two faces. right? It will reflect brain phenomena quite beautifully, and also a very good, artificial AI. Now, if you look at the uh, status of brain theory, right? Thing is, the sensory motor function is the easiest to understand, because how does vision work, how does touch work, and how does audition work? But here itself, we have huge challenges, a lot of gaps, and a little bit of decision making and cognition people have done. But beyond that, if you look at areas like limbic system, the part of us which process emotions, I mean, it's a black hole. There are again small pockets of progress, like fear conditioning and Joseph Leduc's work and so on. But otherwise, we don't have anything like a grand theory of emotions. I mean, psychology described has very beautiful stuff on emotions, like the Plutchik's color charts and all that. But we don't have a good theory of emotions. So I think brain interacts with three worlds. One is the external world, which is where your sensory input all that comes from. Then the internal world, right? The internal organs of the body. How does brain talk to them? But this is called interoception. We call perception when stuff comes from outside. Interoception is when information is coming from inside the body. So that interaction between brain and those different internal organs, that's a hot thing now. And I think with this oscillator theory, you can make a lot of progress there also, I believe. Right, for example, how does brain and heart interact? Heart is operating at 1 hertz, 72 beats per minute, right? Roughly. And how do you interact? How does this big oscillator system interact with that tiny oscillator system? Similarly, gut-brain axis. So we have proposed a theory of how you can naturally bring in gut into brain function, because of reward processing and all that. We propose a theory, like verbal theory, not really mathematical. So that can be extended for. Or similarly, brain-pancreas interaction. If you understand how brain controls pancreas, it might give new insights into diabetes, the disease process of diabetes. So if you can develop these large-scale models of the brain, you can develop better disease models. And then you can cure disease, come up with better cures of disease, more logical cures. But I joke with my students. Look, I mean, you try to get disease in any domain, but don't try to get a neurological disease, because the treatment you get will be, okay, somewhat, very empirical. I mean, it's not based on any detailed logic, right? So thing is, I'm imagining kind of centers, right? Research centers, very small research centers, focused research centers, where this kind of a theory becomes the core activity. And around that, you'll have a pool of experts related to one disease, like a center for Parkinson's, center for Alzheimer's, right? Where you develop the core theory, a deep theory, and around that you have a network of experts and clinicians and all that, and develop applications for that theory, for that disease, right? And that becomes the center's mandate. So like that, it will be nice to have lots of centers. So talking about your AI and applications in medicine, right? You were mentioning that before. One, like, and you also said that people take a very kind of a short-term view and you don't look at a holistic approach and all that. So what happens is, because there's a pressure to do something, startups and so on, we do what is easy and immediately possible. But that won't solve the long-term problem. One has to put in 10, 20 years of effort to understand brain sufficiently deeply. And after that, you will have like an explosion of results. But somebody has to put in that, take that long-term approach. So if you understand brain deeply and develop the right disease models, that will revolutionize it. Otherwise, what happens is, you're always working in short term. You're always blowing up money. Your huge clinical trials turn up inconclusive and are just a failed studies. There's so many of them. What is the point? Right? Don't you want to do the right thing and go for the long haul and just get it done with? Correct. So it's a question of, it's a choice for the policymakers and also for academics, but it's a different matter. So we are working on we have a network of collaborations. Recently, we began collaboration with this Professor Buzaki's lab in NYU. I also visited Allen Brain Institute. Right, several people show interest in collaboration, but the only thing is I don't have that many students to work on all those projects. Then Mount Sinai, we got a contact, we began a conversation with them. We have a long-term collaboration with the INRIA in Bordeaux, France. Dr. Frederick Alexander is a good friend of mine and a long-term collaborator. But it's still a small network. I mean, I'm working hard to grow it as rapidly as possible. But I think main thing is, if some of these ideas can kind of percolate in the field, and problems that are highlighted, people become slightly more conscious of them. people might try different directions. So what matters is not what we and our network does, but if people can become conscious of the bigger problems, then there'll be a lot of geniuses out there and who will take it up and make some rapid progress. That's all I can say.
Lovely. Thank you, Professor. Really appreciate you taking time and being part of the podcast. And you have been at it for the longest time. And we need more such minds, and who are in for the long haul. I think of culture or investment culture or policy culture, we looking at instant gratification. I guess that's the reason we all talk about how we need to emulate the Silicon Valley entrepreneurial the way they work. But the only way we can do that, emulate that culture of creating the rapid innovation is changing our mindset. And I guess going beyond the structures, getting out of those boxes or the structures that we create. Okay, this is what, because I think the future is moving so fast, and we are building things, creating innovations which I think will challenge our perceptions about who we are, who are our creators, and we need to go beyond rather than get caught in these religion, politics. The world is our playground today, and the ones who understand that will be creating solutions which will, I think, change the future. I mean, completely. And the future will not look back, and say, this generation kind of didn't take that opportunity, but say that this generation actually created a better planet. And I hope that happens. And I'm very happy and privileged to have a conversation with you, that you are playing that role, and wish you the very best. Thank you again for taking time being part of the podcast. And to my listeners, if you like what you see and hear, then please press the subscribe button. And until next time, see you guys. Bye-bye. Thank you.
Thank you very much.